IB, HLAA, complex numbers, and more. Day 1 topics for today are an introduction to the complex numbers as well as the binomial theorem. Here you'll see Cartesian form for a complex number. Complex number z takes on the form a plus bi, where the real portion of z is a, the imaginary portion of z is b, and I should note that a and b are in the real numbers. So then the binomial theorem, you'll see it down here. We'll get into that when we get to that page of the notes, but that's a way of expanding this binomial a plus b to the nth power. So let's get right into it. All right, so let's dive right into this. Mathematicians define the imaginary unit I such that I squared is -1. Therefore, we determine that I is equal to the square root of -1. So I want to work a little bit with characteristics of imaginary numbers here, raised to separate powers, and work through a little bit to get you comfortable with this idea of the imaginary unit. So with this in mind, find the simplest expression in terms of I for each of the following. Feel free to pause the video and come back and watch and walk through these. So I cubed, when I use powers and exponents, I could rewrite I cubed as I squared times I. And I squared is -1, therefore I cubed could be written as -I. I to the 4th can be rewritten as I squared times I squared, which would be -1 times -1, which is 1. Now when we look at imaginary units, I'm going to rewrite each of these consecutively, the first 4 powers of I, and then we'll look at how this pattern continues. Okay, so what we see here is that our first term is I, our second term is -1, our third term is -I, our fourth term is 1. That same pattern will be repeated, so I to the 5th will be the same as I to the 6th will be the same as I squared, I to the 7th will be the same as I cubed, I to the 8th will be the same as I to the 4th. So you can see how that pattern will continue, and we can then adjust and look at increasing powers on I. So I to the 7th will be I to the 4th times I to the 3rd. We already looked at this, but I to the 4th is 1, and I to the 3rd is -I. Therefore, I to the 7th is the same as I to the 3rd. Whoa, that's a weird 3. That's better, which is equivalent to -I. Okay, so I to the 7th was -I. I to the 17th would be the same as I to the 4th to the 4th times I. Well, I to the 4th is 1. 1 to the 4th is 1 times I. Therefore, I to the 17th would be the same as I. I to the 27th would be I to the 4th. Notice how everything hinges on I to the 4th. That'll be I to the 4th to the 6th power times I cubed. And of course, I cubed is equivalent to -I. I to the 37th will be I to the 4th to the 9th times I. And therefore, we get a positive I, which is equivalent to I to the 37th. So go figure, when we add these up, we get 0. Very interesting. All right, let's take a look at this example here at the bottom. Now we've seen the notation that you see here in the numerator. This is the sum of the first 2019 terms. I to the 1st, I to the 2nd, I to the 3rd, I to the 4th, all the way up to I to the 2019th. So let's define this as I plus I squared plus I cubed plus I to the 4th, all the way out. Let's go I to the 2015, I to the 2016, I to the 2017, I to the 2018. And of course, our last term, I to the 2019. Okay, there's our numerator. That's the sum of the first 2019 terms. Now, what we'll notice is that the first four terms, I, -1, -I, and 1, those will reduce to 0. Now, as we go along, that will happen a lot of times. So many recurrences. Okay, we'll see that a bunch of times, and then we'll see it for the, oh boy, I don't know how many times that would happen. Let's calculate that. Okay, I miscalculated there. That would happen and end right here. So I to the 2013th, I to the 2014th, I to the 2015th, and I to the 2016th would end right there. That would be the 504th time that would happen. Okay, that leaves us with these last three terms. Okay, these last three terms. Now, when the pattern continues, what you'll see is that I to the 2017th is going to be equivalent to I to the 2018th will be equivalent to I squared, I to the 2019th will be equivalent to I cubed. Therefore, I would have I minus 1 minus I. So it looks like the numerator, if I were to add all those zeros up, I would see that I and negative I reduce, so I get a -1. Okay, all right, let's take a look at the denominator. All right, now this is slightly different. So this symbol here is a pi, so this means the product of the first 2019 terms. So this is going to be equivalent to, let's change colors here, I times I squared times I cubed all the way out to I to the 2019th. So if you consider rules of exponents, this will be I to the 1 plus 2 plus 3 up to the 2019th. Now this series in the exponent here is going to be equivalent to an arithmetic series, right? So I'm going to find the sum of the first 2019 terms. Well, that's the number of terms divided by 2 times the sum of the first plus the last. And my highlighter, I didn't go far enough. Let's see. Oh, that's just devastating. Okay, whatever. So I'm going to find that exponent. Let's do that. So this will be equivalent to half of 2020, which is 1010, times 2019. So we're going to get 2,039,190. Okay, now what I'm going to do, seeing that this is now I to that number, I'm going to divide that by 4. And it comes out to be, this will be I to the 4th to this number, 509,797 and 1/2. So this will be equivalent to 1 to the 509,797 times I squared, which will be -1. Interesting. What that tells us is that I to this power is equivalent to I squared. Crazy. Okay, so our numerator was a -1. Our denominator is a -1. Therefore, our original expression comes out to be -1 over -1, which is 1. That's just craziness. That's our answer. Okay, let's look at a few more examples here. Okay, let's look at identifying the real and imaginary components for each of the following, then graphing them on the complex plane. Now, just a side note, the complex plane is referred to as the Argand diagram. Okay, so let's identify the real and imaginary portions. So the real portion of z is a -2. Imaginary portion of z is a 4. Real portion of w is a 0, and the imaginary portion of w is a -3. Oops, no I attached. All you do is attach the real number coefficient for the imaginary component. Okay, so the real number, or the real portion of psi, is going to be the real portion of z minus the real portion of w, which will be -2 minus 0, which is a -2. The imaginary portion, or component, for psi, the Greek letter, or the Greek complex number, will be 4 minus a -3, which will be a 7. Now, beta, if I want the real portion of beta, what I'm going to have to do is I'm going to multiply z by w. So I'm going to find beta, I'm going to take z, which is -2 plus 4i, and multiply it by w, which is -3i. What I have as a result would be a positive 6i minus a 12i squared. Now notice how the imaginary component is attached to the I, and I squared is -1, therefore -12 times -1 is a positive 12. So the real portion of B is 12, or beta, and the imaginary portion of beta is 6. Okay, so let's plot each of these. We'll plot Z, and we'll plot W, and we'll plot psi, and we'll plot beta. So Z, on the real axis, we would go left 2 and up 4. So this would be the location of Z. Okay, also on the Argand diagram, let's plot W, -3i. It has no real component. There will be no horizontal movement. That'll be W. Okay, psi, we're going green. So a -2 for the real component, a 7 for the imaginary component. We don't have that on our Argand diagram, but here's where psi would be. And beta, the real component of 12, imaginary component of 6. Let's go way out here to our real component of 12 and our imaginary component of 6. That would be beta. That's how you plot based on a very inaccurate Argand diagram, which did not expand to the values that I intended it to, so my bad. Let's continue with more on complex numbers. All right, next topic is the modulus, or absolute value of a complex number. Notation referred to here would be absolute value of the complex number z. Right, that's referred to in mathematical notation in that way, is the distance from the complex number to the origin. So if I were to generally plot a complex number here on the imaginary, real and imaginary axes, which is considered the complex plane. Here is A, our real component, here is B, our imaginary component, so here would be Z. So the modulus, right, of the complex number Z, or also referred to as A plus BI in Cartesian form, is going to be the distance from the origin. Here's the origin, O, we typically call it, out to Z. And of course, what we do to find that length is we would use the Pythagorean theorem. Clearly you can see here the square root of a squared plus b squared, or the square root of the real component squared plus the imaginary component squared. So that's how we find the modulus of a complex number, also referred to as the absolute value. Now, the argument of a complex number is the angle of rotation from theta equals 0 to the segment representing the modulus. Therefore, what you'll see here, again, generally speaking, real component, imaginary component, complex plane. Here I've got my complex number in a general form, a plus bi, of course, in Cartesian form. Here is our modulus. Our argument is the angle of rotation right here. So the argument of z. The argument of z, if this is b and this is a, of course, will be the inverse tangent of b over a. Or in other words, in more general terms, the tangent of the argument of z is equal to b over a. Of course, we're dealing with right triangles, therefore all right triangle trig applies. Okay, so what is the argument? The argument is simply this angle, sometimes referred to as theta, but typically referred to as argument of z. Now, in many cases, the principal argument may be requested. Okay, and the principal argument is bounded by negative pi to pi. Therefore, an answer like, let's say 5 pi over 4 could not exist as an answer if you're prompted for a capital A argument of z. Okay, since that does not land within the principal argument range. Therefore, what you would do, of course, you can use your right triangle trig. Here would be that angle of rotation. Right, that's where 5 pi over 4 lands in quadrant 3. What I would do is find a coterminal angle which fits the principal argument range, which in this case we would then say that the argument of z would be negative 3 pi over 4. So just beware along the way that the principal argument is sometimes requested, utilizes the capital A in argument, and requests within an angle within this range here. Okay, let's continue with more on complex numbers. All right, looks like we're going to be finding modulus and argument. Okay, so first thing I like to do when finding the modulus and argument is I'm definitely hoping that the values that I'm given are unit circle friendly, because we can just plot the unit circle right on the complex plane and continue to work with the ratios that are given. So whenever I see A and B, whether their signs are the same or not, if their values are the same, then I know I'm dealing with some form of pi over 4. So let's plot z on the complex plane real quick. So it looks like we're going to be headed to the right 12 and down 12. So let's go right 12 on the real portion of the complex plane. Let's go down 12 on the imaginary portion of the complex plane. All right, that puts our point here. This is z. Of course, here's our modulus. This would be 12 root 2. These are unit circle friendly numbers. Okay, so our modulus is 12 root 2. The only reason I knew that is because I know that if I have a 1, 1 root 2, that's a 45, 45, 90. Right, we're the isosceles right triangle. So all I did was multiply that by 12, and I got myself the triangle we're working with here. So we could say that the modulus of z is 12 root 2, and the argument of z is going to be negative pi over 4. Typically, we're going to work in radians, so maintain that as you work throughout. Okay, cool. Let's look at the complex number m. Looks like we're going to be moving left, real component is negative, and then up. So we'll be in the quadrant 2 of the complex plane here. There's c. Here's our imaginary component of m. Here's our real component of m. Left 1/2 and up root 3 over 2. That looks very friendly to us. I think we've seen those numbers before. Our modulus here is going to be 1. Right? You either use Pythagorean theorem or special right triangles, but our modulus of m is going to equal 1. Our argument of m is going to be this angle of rotation right here. Now, I know this angle right here is a 60-degree angle, or pi over 3. Therefore, our argument is going to be a positive 2 pi over 3. Okay, let's look at something a little bit more abstract in the third example. All right, so here we have a complex number w. All right, and generally speaking, I'm just going to put this in quadrant 1. Okay, so here's our real component of w, imaginary component of w, and here is w. So our real component, red, was cosine theta. Our imaginary component in blue was sine theta. So our modulus, interestingly enough, all right, the modulus of w is going to be equivalent to the square root of the real component squared plus the imaginary component squared. Well, we know from some trig that we studied, I don't know, someday, that sine squared plus cosine squared is 1, and the square root of 1 is 1. So the modulus here is again 1. Now, as we look at this, to find the argument, okay, so let's call this theta, our argument of w, we could say that the tangent of the argument, we haven't done this up to this point using the tangent of the argument, but the tangent of the argument is going to be equivalent to the tangent, the sine of theta over the cosine of theta. Okay, so we're working in general terms here, but what you'll see is that this statement right here, or expression here, is equivalent to the tangent of theta. So the tangent of the argument of w is equal to the tangent of theta. Therefore, the tangent of this angle makes the two angles the same. Nothing real groundbreaking there. But what you'll see in the homework is actually, I'm going to flip these two on you. All right, I'm going to say the real component is sine, the imaginary component is cosine, and I want you to work through that and see if you can come up with a response for the argument of that complex number. So it'll get kind of interesting, but use your properties of trig, maybe a little cofunction identity or two, and you'll see what happens. So let me know if you got questions on that. We can definitely walk through it. All right, let's do a little bit more. We got a few more slides here. All right, for any complex number in the form a plus bi, which we know is Cartesian, where a and b are in the real numbers, there is a conjugate complex number referred to and noted as z star, which is equal to a minus bi. So we change the sign of the imaginary component. Their real parts are equal, as you can see. Up here, a is no different, but their imaginary parts are opposite. So the imaginary portion of z is equal to the opposite sign of the imaginary portion of its conjugate. Conjugate complex numbers are useful in many ways, and you'll see that later on, but one of them is when dividing complex numbers. So let's take a look at an example below. I'm given the complex numbers z and w. Find the real and imaginary components of 5w over z. So when I take z over w, 5w over z, what I get is negative 15i over negative 2 plus 4i. anytime you're asked to put this in Cartesian form, which it's not yet, the denominator is in Cartesian, so is the numerator, but the rational expression is not in Cartesian form. We got to get rid of the rational portion. So what we're going to do is we always multiply by the conjugate of the denominator. Conjugate of the denominator is the same as the numerator, same as the denominator, except we change the sign. So you can see I have a negative 2 plus 4i, therefore I have a negative 2 minus 4i. So I'm going to multiply top and bottom by that. So as I expand this, in the numerator I get, positive 30i plus 60i squared. You'll see that my real and imaginary components kind of flip locations. We'll get those back in order in just a minute. Now when we FOIL conjugate, something interesting happens. You'll see it as we go. Negative 2 times negative 2 is a 4. Negative 2 times negative 4i is a positive 8i. 4i times negative 2 is a negative 8i. And 4i times negative 4i is a negative 16i squared. So what you'll see is the imaginary components, they always reduce. Okay, so I'm going to rearrange the numerator. And I squared I know is negative 1, so I'll have negative 60 plus 30i, and you'll see what I get in the denominator in just a moment here. Okay, so let's take the denominator over here. This is 4 minus 16 times a negative 1. Well, that's going to end up equaling 20, which is great. Makes this very simple. And therefore, 5w over z is equal to negative 3 plus 3i over 2. And therefore, the real portion of 5w over z is equal to negative 3, and the imaginary portion of that same complex number is equal to 3/2, or 1.5. Okay, the more practice you get with working with conjugates, the better you'll get at it. All right, let's continue to another example. Okay, example 4. Given the complex number a plus bi, again, where a and b are in the real numbers, find the relationship between a and b such that the following are true. Okay, so first you got to figure out what the heck this is asking. This is saying take z over 2 plus I. Well, what is z? Z is a plus bi over 2 plus I. And what we want to do is we want to find the relationship between a and b such that this number is real only. Right? Therefore, the imaginary portion of this number, right, z over 2 plus I, is equal to 0. There is no imaginary portion. So let's go ahead and work with the conjugate here real quick. Let's multiply top and bottom by 2 minus I. Okay, and I'm going to show you a shortcut along the way. All right, so I would get 2a minus ai plus 2bi, and that would be minus bi squared. Okay, in the denominator, what I'm going to get is 4 minus 2i plus 2i, and a minus an I squared. Okay, now, anytime you take z times z star, which is what you'll do in this case, right? Z times z star, or whatever it might be. What you're going to actually get is you'll always get the magnitude of z squared, right? So what would be the magnitude of 2 plus I? Okay, what would be the modulus, right? Well, that would be the square root of 5. Well, if I squared it, what would I get? I'd get 5. Check out what I'm about to get here. Okay, let's combine some like terms. Okay, so I'll have my real component will be 2a plus b. 2a plus b, and I'm going to put parentheses around that to remind me that's my real component. Plus, check this out, I'll have 2b minus ai. Okay, and that's all going to be over 5. Cool. Okay, now, so here's what we want, right? We want the imaginary portion to be 0. Well, if the imaginary portion is 0, right, what I'm going to do, I'm going to set the imaginary portion to be minus a equal to 0 and find the relationship. So in order for this to be true, a has to equal 2b. If a equals 2b, then the imaginary portion of z over 2 plus I is equal to 0. Boom, there it is. Okay, let's look at example B here. And this is asking us actually the opposite, right? It's asking us for what relationship here is this complex number, this expression, purely imaginary. What that's saying is find or show the relationship between A and B such that the real portion of 1 minus I over z star is equal to 0. So if the number is purely imaginary, there's no real component. Okay, so let's go here. And of course, what we know is we're going to multiply this by its conjugate, which is just z. Now check this out. This will be kind of cool. We know that z star times z, right, is going to be the same as the magnitude of z star squared, which is actually the same as the magnitude of z squared. That's a property that I'll show you in a separate video. Okay, so if I have a minus bi, and I want the magnitude of that, that's just going to be the square root of a squared plus b squared. And therefore, squaring that, I would just get a squared plus b squared. Okay, so what I'm going to get is, of course, I'm going to have, I got to expand the top here. 1 minus I times a plus bi over a squared plus b squared, which actually won't even matter. All that I want to do is take the real component, set it equal to 0. So let's see what we get for the real component here. That'll be a plus bi minus ai, and then plus b. Now, how did I get plus b? Well, I took negative I times bi, which is negative bi squared, which is a positive b. Okay, therefore, and of course, that's over a squared plus b squared, which is irrelevant, but we'll write it down. That'll be a plus b, real component, plus b minus a, I, all over a squared plus b squared. Again, irrelevant to our problem, but we're going to write it to be thorough. Therefore, I'm going to take the real component, which I guess would include the denominator, but in this case, all I care about is the numerator. And I'm going to say that a plus b is equal to 0. Therefore, if a equals the opposite of b, then our original expression, 1 minus I over z star, is purely imaginary. Cool, there it is. All right, 2 more slides to do it. All right, the binomial theorem is shown below and is used for binomial expansion of the form a plus b to the nth. Now, this is not a complex number. I know my notes might make it look like it, but this is just a real number or variable plus a real number or variable. So whatever the expression might be, it could be an imaginary number, or excuse me, complex number, but it doesn't have to be. So you can attach an I to either of those terms, doesn't matter. Okay, here is the general expansion. All right, you're going to take a to the nth plus n, choose 1, a to the n minus 1th, b to the first. So what you're going to see is a descending power on a. So a to the nth, a to the n minus 1th, a to the n minus 2. Then you'll see you have a to the first, then a to the 0. Now this has a b to the 0, then b to the first, b to the second, blah, 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 b to the n minus 1th, b to the nth. Now in addition to that, we have the combination expansion, right? So NC1 or NCR is n factorial over n minus r factorial, So if I took NC0, that would be n factorial over n factorial, which is n minus 0, times 0 factorial. Well, n factorial over n factorial is 1, and 0 factorial is 1, therefore I get a 1, and that's why you don't see it, but it's right there. Okay, now you can use combinations in order to do binomial expansion. You can. You don't have to. What I actually prefer to do is I prefer to use Pascal's triangle. And in Pascal's triangle, what you're going to see is that you have this triangle that increases each row you go down, it increases by one block, if you will. So I'll explain here in a second. You've probably seen this before, but might not have remembered it. Okay, so this is useful in probability, it's useful in binomial expansion, and the numbers continue to go in this way, in the same pattern. Okay, so this is the what we call the 0 row. This is the 1 row, 2 row, 3 row, 4 row. You can identify the row number here by, like you can see row 2, row 3, it's always the second number in that row, or the second to last number in that row. Now these two, well, you just start at 0. Okay, so let me show you how to use Pascal's triangle, this thing, to come up with binomial expansion. First of all, let me show you just one of the items here that you might want to be aware of. Okay, so this number right here, that number right there in combinations is row 3, choose 1. Okay, so here's row 3, this is my n, and choose 1, this is my r. So your first number in the row is always choose 0. So like if you had 3 objects and you choose 0 of them, there's only one way to choose that. If you have 3 objects and you choose 1 of them, there's one way to choose that. If you have 3 objects and you choose 2 of them, there's 3 ways to choose 2 of them. And if you have 3 objects and you choose 3 of them, there's only one way to choose 3 of them. Okay, so this number right here, go ahead and take a guess at what that would be in combination notation. Okay, so now you've guessed. That would be 4 choose 2. 4 choose 2 is 6. Okay, so now you see how Pascal's triangle can be a quick way to not have to use factorials. Nobody wants to use factorials if they don't need to. Okay, so let's expand the following 2 binomials. Okay, so notice that each row of Pascal's triangle starts with a 1 and ends with 1, right? And all the numbers in between are built by the numbers above it. So you can see that 1 plus 2 makes 3, 2 plus 1 makes 3, 3 plus 3 makes 6, 1 plus 3 makes 4, 3 plus 1 makes 4. So the number right here would be 4 plus 6, which is 10. So you would have a 1, 5, 10, 10, 5, 1. Okay, so let's build 2 plus I to the 4th. Okay, so I'll always start with a 1, then I'll have 2 to the 4th, and I to the 0. Now, since this is the 4th power, I'm going to go to the 4th row. So my next coefficient will be a 4, 2 to the 3rd, I to the 1st. Oops, 1st. My next number coefficient will be 6, 2 to the 2nd, I to the 2nd. Next coefficient 4, 2 to the 1st, I to the 3rd. Next coefficient 1, 2 to the 0, I to the 4th. notice the coefficients when your power is a 4. 1, 4, 6, 4, 1. Okay, now let's combine the like terms. So our first term will just be a 16. Our second term will be 32i. Our third term, I squared is negative 1, therefore this will be negative 24. Our fourth term, I cubed is negative I, therefore we'll get negative 8i. And our last term will be I to the fourth, which is 1 times 1 times 1, which is 1. Therefore, 2 plus I to the fourth power using binomial expansion comes out to be, oh boy, negative 8, negative 7 plus 24i. There you have it. That's 2 plus I to the fourth power. I'm going to go off screen. I'm going to let you expand the second one, and I'll come back and show you my answer. All right, so check it out. I went to the fifth row of Pascal's triangle. Here are my coefficients, 1, 5, 10, 10, 5, 1. So I've got 1, 5, 10, 10, 5, 1. Descending powers on the 1 to the fifth, negative 3i to the 0, 1 to the fourth, negative 3i to the first, 1 to the third, negative 3i to the second, 1 to the second, negative 3i to the third, 1 to the first, negative 3i to the fourth, 1 to the 0, negative 3i to the fifth. Now, once you get comfortable with this, you might not need to include, your to the 0 terms, nor do you need to write to the first power, right? Once you get comfortable with it, expand, work out your terms, find the real and imaginary components if it applies, if there's a complex result, and then you've got your answer. I got 316 minus 12i. Pretty sure I did my algebra correctly there. And that's it. That's how you use the binomial theorem. We got one more question here, or two more examples, excuse me. Kind of some side examples on how to use properties of complex numbers, and then that'll be it for today. Let's check it out. Okay, examples 6 and 7 are unique uses of what we've just learned, so let's go ahead and jump into them. Simplify the complex number, converting it into Cartesian form. So 1 plus I cubed and 1 minus I cubed. Let's expand each individually. I'm going to do the numerator here. I'm going to use my knowledge of Pascal's triangle. So this will be, of course, to the third. I'm going to use the row 1, 3, 3, 1. This is row number 3 in Pascal's triangle. I'm going to use it for both, actually. That's great. So my first term will be 1 times 1 to the third times I to the 0. I'm not going to include that. Plus 3 times 1 squared times I. Plus 3 times I to the, 1 to the first times I to the second plus 1 times I to the third. Okay, so that'll be the expansion of the numerator. Expansion of the denominator will be very similar. It'll be 1 plus 1 cubed plus 3 times 1 squared times a negative I to the first plus 3 times 1 to the first times a negative I squared plus 1 times a negative I cubed. Okay, so let's do a little work on that. Numerator. Okay, first term becomes 1. Second term becomes 3i. Third term becomes negative 3, right? 3 times I squared. And the last term becomes a negative I. Right? I cubed is a negative I. Denominator, of course, we'll have 1. We'll have a minus 3i. Third term in the denominator. Negative I squared is I squared, which is negative 1, which will be negative 3. And the last term will be negative I cubed, which is the same as negative I, which is a positive I. Thus, in Cartesian form, let's see what we get here. So numerator will be, looks like negative 2 plus 2i And in the denominator, we will get negative 2, and it looks like a minus 2i. All right, looks like we have a little bit more work to do, but I can. This will be a negative 1 plus I. Let's reduce it over negative 1 minus I. Okay, so it looks like we have conjugates, and this will be interesting. Okay, so I'm going to multiply by the conjugate of the denominator, which actually ends up being the numerator. So it'll be negative 1 minus I, plus I. Negative 1 plus I. Okay, so I'm going to use my shortcut here. Conjugates multiplied together will be the same as the modulus of the denominator squared, right? So if I multiply the denominator together, of course, the modulus of negative 1 minus I is going to be the square root of 2, right? So if I squared that, I'd get 2. So the denominator will be 2. The numerator, on the other hand, will be a positive 1, and I'll get a minus I, I'll get another minus I, and I'll get a I squared, which is negative 1. Therefore, I get negative 2I over 2, which is equal to negative I. Thus, in Cartesian form, the original is equal to 0 minus I. Very interesting. Okay, let's look at example 7, and that'll be it for today. It says evaluate the following. Leave your answer in Cartesian form. The square root of a complex number. What the heck? Okay, so let's call this complex number z, right? And I want to find a plus bi, right? The a plus bi Cartesian form of this answer. Well, I think we can all agree that z squared would equal 7 minus 24i. So generally speaking, let's let z equal a plus bi. So let's write that in, substituting in for our complex number z, a plus bi. 7 minus 24i is equivalent to a plus bi squared. Okay, so that would be a squared. All right, if I square this binomial, right, plus 2abi plus bi squared. That should equal 7 minus 24i. Now I did a little shortcut there. I used Pascal's triangle, right, and the binomial theorem to expand that left side, but you get that, right? Bi squared is going to be the same as negative b squared. Now look, I have my real and imaginary components here. Okay, so I know a squared minus b squared equals 7. And I know 2ab is equal to negative 24. So I just need a negative 24 there. Okay, so I got a little bit of work to do here, but check this out. This is kind of cool, right? So a is equal to negative 12 over b. So I'm going to sub that in here. Negative 12 over b. And I'm going to solve for b, and then I'm going to use that to plug back in and solve for a. So it'll be 144 over b squared is, minus b squared is equal to 7. Okay, now I'm going to multiply all terms by a b squared. That'll clear the fraction. That'll give me 144 minus b to the 4th is equal to 7b squared. Okay, let's do a little work over here. So 7b squared. Oops, I didn't want to do that. Let's do this. Let's move everything to the left side. So that would be b to the 4th plus 7b squared minus 144 is equal to 0. Okay, now I'm going to do a little factoring. Okay, so how can I get 144? Well, I'm going to have, Of course, since the two numbers that I'll have here have to add to 7, but multiply to negative 144. I'll have a positive and I'll have a negative number. Okay, so let's do a little factor. Okay, so I found that 9 times 16 equals 144. And those two are separated by 7 units. Therefore, I'm going to want to have 16 here and 7 there. Okay, so, oh, excuse me, and 9 there. How about a 9, not a 7? Okay, perfect. Therefore, 16 times negative 9 is 144, and 16 plus negative 9 is a positive 7. Outstanding. Now check this out. If this is to be true, then that means b squared equals 9, or b squared equals negative 16. Well, we know that b has to be in the real numbers. Even though it's the imaginary component, b has to be in the real numbers. Therefore, this right here could not have a solution. Thus, b equals 3 or negative 3. So if b equals 3, let's write out the two possible. Let's say that b equals a positive 3. Well, if b equals a positive 3, then a equals a negative 4. And if b equals a negative 3, then a equals a positive 4. There are your two answers to the square root of 7 minus 24i. Alright guys, that's it. That's complex numbers intro. Kind of a long video, but we'll have some time to recoup and relearn if necessary and get solid with some of these properties. So we'll see you in the next video. Have a great day.